And welcome to video 23.3. We're going to be looking at the electric field due to point charges. So we're moving away from the definition of electric field, which is expressed in terms of the force on a test charge, and are moving toward a way of calculating the electric field due to the source charges. So recall that we defined electric field as the ratio of the force on a test charge to the test charge itself, F over Q naught. Now let's say that the charge that is producing this electric field is a single point charge Q. So Q is right here. It produces an electric field, and let's say that we put a test charge, Q naught, at a point a distance r away from big Q. Now because they're both positive, the force on this test charge will point away from big Q. And if we calculate the magnitude of that force, it's K times big Q times Q naught divided by r squared. If we calculate the electric field at that point, then it will be F over Q naught, which is equal to K times big Q over r squared. And we notice that that expression is independent of the test charge. And that means there would be an electric field at that point in space with this value, even if there's no test charge at all. And we're going to use that to calculate the electric field. So given a collection of point charges, find the electric field that is created by those point charges. And if we have multiple point charges, all we have to do is find the electric field for each point charge and add all the fields up. So let's say that we have 3 point charges, Q1, Q2, and Q3. And we want to find the field at this point here. I'll call that point P. Well, what we do is we say, well, Q1 produces let's say Q1 is positive, Q2 is negative, Q3 is positive. Q1 will produce an electric field, E1, that points away from Q1. Q3, also being positive, will produce an electric field, E3, that points away from Q3. And Q2 will produce an electric field that points toward it, because it's negative. Now, if you add all of these up, the net field is just the vector sum of the 3 individual fields. And in principle, it's very easy. In practice, it can get very, very complicated because adding vectors is not always simple. But most of the problems you'll actually have to do are quite straightforward. Just drawing connecting lines so that it becomes more obvious the directions of the forces. So here's an example of something you might actually have to do. It's problem 11 from your book. You have a collection of 4 source charges. You've got plus 5Q here, plus 5Q down here, plus 3Q, and minus 12Q. And they're all separated by a distance d from other things. And we're trying to find the field at x marks the spot at point P. Now if we draw the magnitudes of the fields, the field due to charge 1 is going to point that way. The field due to charge 2 will point away from charge 2 because it's positive. It points that way. Field due to charge 3 will point away from charge 3. And the field due to charge 4 will point toward charge 4 because charge 4 is negative. So first we're going to look at the magnitude of field E1. And it's equal to K times the source charge 1, which is 5Q, divided by the square of the distance. And it points in that direction. Now if we look at the field E2, we find that it is also K times 5Q because charge 2 is also 5Q, divided by a squared, and it points in that direction. So we notice that E1 and E2 have equal magnitudes in opposite directions. And so that means that E1 and E2 cancel out. And so we can ignore them. We say the net field E1 plus E2 plus E3 plus E4 as vectors. Those two cancel out. So now let's look at E3. It's K times Q3 is 3Q divided by, I shouldn't be using D, I should be using D. Fortunately, A's are easy to turn into D's. So this is divided by D squared. And it points in that direction. And last of all, E4 is K times 12Q. Remember, we're not putting the negative in here because the direction is given by the geometry. But the distance to E4 from point P is 2D, which needs to be squared. And when you work this out, it works to 3KQ over D squared, and it points in that direction. So we notice that E3 and E4 also have equal magnitudes and opposite directions, so they cancel out as well, and the net field at point P is equal to 0. What that means is that we could put any charge we wanted at point P, and that charge would not experience any force at all. The other four charges would, but we don't care about them because they're source charges. Now, most of your problems aren't going to turn out to be that easy, but they will generally have convenient geometries like this so that you don't need to do a whole lot of nasty vector stuff. Tomorrow we're going to look at questions 2 through 4, or I'm going to look at questions 2 through 4, which means you need to do them tonight.